All right, so here are a few problems for the Unit 6 homework on thermodynamics and heat. And I'm going to start out with these two problems here. Number 12, how large an extension gap, and number 15, show that, and so on. And by the way, these two problems will be relatively similar because the equations are relatively similar. So in case, here's the first one. So how large an expansion gap should be left between steel railroad rails if they may reach a maximum temperature of 35 degrees Celsius greater than when they were laid? The original length is 10.0 meters. And here we would have assumed that they're actually being laid down when it's really cold. And then now you have a hot summer, 35 degrees warmer. All right, for that we need to look up the thermal expansion coefficient for steel. I'm going to do that for a moment. Actually, I think if I scroll up here, I should get there. Let's see, here we go. Okay, so it's in this big table here. We're looking for steel. So 12 times 10 to the negative 6, that's the linear expansion. So I'm going to plug in the numbers that are given here, which is that expansion coefficient, 12 times 10 to the negative 6, times, oh actually I would like to look at the numbers. There we go. 35 and 10, there we go, times 10.0 meters. And I know that I want too many times there. There we go. Times 35 Celsius degrees. And that comes out to 0.0042 meters. Okay, I said the other one is actually relatively similar here, so show that 60 liters of gasoline originally at 15 Celsius degrees will expand to 61.1. Okay, so I'm supposed to show that also when it warms to, from 15 to 35, so 20 actually. And so I'm going to go to the same table here, and here I have to actually look for gasoline. Okay, I guess we're going to use petrol. And notice they don't have any liquids, and gases don't have any linear expansion coefficients. They only have volume ones, which makes sense because when they expand in all directions. While you could have a bar of something like the railroad that expands mostly in the length. Okay, so here we go. I need the 950 times 10 to the negative 6. Go back to the problem, so I see the numbers. And no, I forgot the number already. Was it 950? Yeah, 950 times 10 to the negative 6. 950, 10 to the negative 6. That expands quite a bit. Times, let's see, the original one is 60 liters. Times an increase of 20 degrees from 15 to 35. That's 1.1 liters more, which means that it increases, from 60.0 to 61.1 liters rounded. The answers are here. There's the 61.1. The calculation here is the same, and then at the end 60 liters added. And then for the previous one, just like I computed, 0.0042 meters, which is actually for a 10-meter long steel railroad rail. There's the word I was looking for. That's actually only 4.2 millimeters. So, but you still have to account for it, because otherwise it buckles, because there would be a lot of tension in those. I'm going to take a little break here. All right, the next two problems I want to do are an airplane passenger, number 29 and 43, the escape velocity from the moon, and so on. So I'm going to go over here. So 29, An airplane passenger has 100 cubic centimeters of air in the stomach just before a plane takes off from a sea level. What volume will the air have at cruising altitude if cabin pressure drops to this much? Typical atmospheric pressure is 101,300 pascals. So they're saying here drop down to 75,000 pascals, which is 25%. I would say that the answer should be therefore 25% larger, so it should come out to 125. Let's see. And I'm going to go over here. This is the ideal gas law. And there it is. That's one version. Pressure, volume, number of molecules times the Boltzmann constant times temperature. And the other version is PV equals nRT. Where's the other one? There it is, PV equals nRT. In any case, in the stomach here, the temperature would be the same. They didn't say anything about the temperature changing. The ideal gas constant is right there, and it says it's the same number, it's the same amount of air in the stomach, which means the same number of moles, so that means only pressure and volume changed, and therefore this becomes relatively simple. And which is actually a special form, one of the special forms of the ideal gas law, which is Boyle's law. And there it is. Okay, so yeah, just like it shows, so apparently not 25% more. Okay, depends on, depends on the algebra. It's actually about 30% more, and just like it shows, 1.013, that's the 101,300, 10 to the fifth, divide by the 7.50, 10 to the fourth, times 100. I think the calculator understands the way I'm plugging that one in here, and sure enough, 135 cubic centimeter. My guess here with the 25% goes off the 101,000 minus 25%, but actually it's the 75,000, that's the base number, hence 35% more. All right, escape velocity from the moon is the next one. And I'm gonna go, here we go. Escape velocity from the moon is much smaller than from Earth, and is only 2.38 kilometers per second. At what temperature would hydrogen molecules, that's the molecular mass here, equal to, have an average velocity equal to the moon's escape velocity? So, I'm going to go here, kinetic theory. And they start out with the ideal gas law, and then go through all the motions here, and apparently I highlighted that here. Basically, this equation says that the temperature is a measure of the average kinetic energy of the molecules that are in a gas. So the 1/2 mass velocity squared, which is the average kinetic energy, and then equals 3/2 times the Boltzmann constant times temperature. All right, and then they're solving here, and that's the equation we need, square root of 3kT over m. And I might as well look at this one here. So plugging in the numbers. Okay, so first we have to determine the mass of a hydrogen molecule, hence the given 2.016 grams per mole, divided by Avogadro's constant, 2.016, grams per mole. Oh yeah, and that's then in kilograms already, that's why there's the -3, divided by Avogadro's constant. And that is the mass of a hydrogen molecule. It's twice the atomic mass unit, which is not surprising because the atomic mass unit is the same as the mass of a proton. A hydrogen atom is basically the proton. Yes, there's an electron there too. And a hydrogen molecule, of course, is twice as much because there are two hydrogen atoms. Okay, that one to be plugged in here and solving for the temperature. So you can follow the algebra here, and then that would be the mass times, I'm just going to say answer times, and let's see, escape velocity 2.38 kilometers per second. That's still quite a bit. So 2,000, I'm going to write, simply going to write 2,380 meters per second, and that needs to be squared. Divide by 3 and divide by the Boltzmann constant. You can see that 1.38 times 10 to the negative 3 is related to Avogadro's constant. It's not exactly the reciprocal of it. There's actually a factor 8.314 involved, which is the ideal gas constant, and I hit enter, and I come up with 458 kelvins. 458 kelvins is actually quite high. That's 185 Celsius, so in the neighborhood of 350 Fahrenheit. And the moon, well, on its day side facing the sun, could actually have that high, and therefore it evaporates all the hydrogen into space. Also, the VRMS, root mean squared velocity, the average, it's an average velocity in a gas. That means that there are also a number of molecules that are just much faster than that, and therefore they would evaporate into space. And that's what happened to the moon. Give it enough time, millions, billions of years, all hydrogen has evaporated into space. The same thing happened on Earth, actually. Our escape velocity is larger, and so it would be that RMS velocity, yes, that it would be the RMS velocity, and so would be the necessary temperature. However, again, there's plenty of molecules that are actually faster, and they have over time evaporated into space. That's also why we fortunately do not have a lot of hydrogen in our atmosphere, because hydrogen really loves to react with oxygen. So, and oxygen, nitrogen, they're a whole lot more massive, so they have a really much harder time to evaporate into space. So our atmosphere is built from nitrogen and oxygen, but if you compare the layer of the atmosphere around the globe of the Earth, it's really thin. So, because again, there is a probability that they do evaporate into space, and what's left behind is a really thin atmosphere. All right, give myself a break here. So here are some problems from chapter 14 in your openstax textbook, heat and heat transfer methods. So number 1 is what I'm going to do. On a hot day, the temperature of a swimming pool and so on. So let's see. Here's the original problem. On a hot day, the temperature of an 80,000 liter swimming pool increases by 1.50 degrees Celsius. What is the net heat transfer during the heating? Ignore any complications such as loss of water by evaporation and so on. So first figure out what the mass is. Well, because the density for water is 1.00 grams per cubic centimeter, it's 1 kilogram per liter. So 80,000 liters as a volume is also 80,000 kilograms, which is what it says here for the mass of that. They do a more complicated calculation here because it's usually not listed as kilograms per liter. It's kilograms per cubic meter, I guess. But in any case, 80,000 liters volume is 80,000 kilograms for the mass because of that 1.0. Okay, then that means that the heat is the mass of the water times the specific heat capacity times the temperature difference. So the specific heat capacity is, here it is, for water, 4,186, and the unit is joules per kilograms in Celsius degrees. And look at the others that are on the list. They're kind of like in the hundreds. Okay, there's one relatively large, that's the human body. Well, we're mostly made out of water, and then there's ice, which is water, and then all the others are in the hundreds. Okay, there's wood and a few liquids that are in the thousand, between 1,000 and 2,000. But notice water has this really high specific heat capacity compared to a number of other common materials, and that is important to us as a species, that water has such a large specific heat capacity. So I need the 4,186. It's already in base units, so it's 80,000 kilograms times 4,186 times 1.5, and the calculation, of course, is exactly that. So I can plug it in here. There we go. So that is the 500 million joules in order to get in there. I converted that to kilowatt hours. So let's look at, here it is. Notice the 139 kilowatt hours. The way to do that is to divide by 3,600, which is for seconds in an hour, and then divide by 1,000 to get it to kilowatt hours, and there we go, 139 kilowatts. Okay, maybe rounded 140. Either way, then the original problem actually says that, well, it's a hot sunny day. I kind of changed the idea here to, well, what if you had a swimming pool in Alaska and it costs you almost $18 for a kilowatt hour? That means in Alaska, you don't have a hot sunny day, you have a cold sunny Alaska day in the summer, so you actually have to heat your swimming pool because it gets cold overnight. And so therefore, in order to actually heat it by just 1.5 Celsius degrees, which is about 2.5 Fahrenheit degrees, would cost you every day $25 just to get it up by 3 degrees Celsius or 1.5, 3 degrees Fahrenheit or 1.5 Celsius degrees. And as I say here, there's a reason why Alaskans don't have swimming pools in their backyards. By the way, the original 80,000 liters here is realistic. If you think of a swimming pool that's 2 meters deep, so 6 feet, 5 meters wide, that's in the neighborhood of 16 feet, and I think 8 meters long, that's in the neighborhood of 30 feet. Yeah, that's quite realistic, and it would be actually 80,000 liters. Okay, I think I'm finally done with this problem. All right, I want to do this problem here next. So number 18, a gargantuan iceberg broke away from the Ross ice shelf in Antarctica and so on. And notice that I gave away the first two answers. And I'm going to cover them here in a moment. And the only answer you have to find is then the number of years. I put a video here that I found world's biggest iceberg heads for potential disaster. It's possibly, I forgot, it might be actually a different iceberg, but that's the video I found. So anyway, it was approximately 1986, gargantuan iceberg broke away from the Ross ice shelf and so on, and 160 kilometers long and this wide and this thick. What is the mass of the iceberg given the density is 917 kilograms per cubic meter, which is less than the 1,000, exactly 1,000 kilograms per cubic meter for water, and hence ice floats. And which is also important that ice floats. So water's high specific heat capacity, and then that ice floats. So gonna plug in numbers here to get the volume. So it says 160 by 40 by 250, and that would be in cubic kilometers, which I now need to get into cubic meters. 1,000 meters in the kilometer, and then of course cube it because of, well, because it's cubic, and then multiply that with the density, so times the 970. Okay, am I making a mistake here? Hold on. Yep, I did find the mistake. The 250 was not kilometers. It said 250 meters thick, so not 250 kilometers. So my end result, or at the beginning, it should have been 0.25 rather than 250, and the way to fix that is divide by 1,000. So there's the 1.47 10 to the 15 kilograms, just like it says in the answer here. All right, and the next part then is how much heat transfer in joules is needed to melt it. Well, for that I need the latent heat of fusion, and in the OpenStax textbook here's the table for that, and water here 334,000 joules per kilogram. Notice it says kilojoules here, but I need it in joules, so 334,000. There are two latent heats, of course, one for fusion, so it's melting or freezing, and the other one here is for evaporation, respectively condensation. And notice among the materials, again, it's a lot for water, 334. If you compare the others here, they all have quite a bit smaller here, except I guess some metals like aluminum here actually has more. Okay, anyway, I need the 334,000, so I'm going to go back to the problem and the calculator. So this one here, simply it's mass times latent heat, 334,000 times that mass. And there we go, 4.9 times 10 to the 20 joules. Notice that they went through the calorie here, so there's a second latent heat of fusion in kilocalories. Notice the 79.8 right there. I didn't need that. Yeah, this actually, the way they did it here is a little bit more complicated. Going through the calories, so I just multiplied with the joules per kilogram, 334,000. All right. Right, so last thing then to do is how many years would it take sunlight alone to melt ice this thick if this ice absorbs an average of 100 watts per square meter? I'm gonna look up the solar constant. Should give us 1,380, 1,370. Let's see, I'm going to click on this one here, and there it is. 1,360 watts per square meter. I know it says kilowatts here, but 1,360. Notice that the problem here actually says 100 watts per square meter, so appreciably less. Well, the thing is, the ice is white, so it's going to reflect most of the incoming sunlight of the 1,360. It's going to reflect most of it and only absorbs apparently 100 watts per square meter. So that's the number we're going to use. And then here, of course, is the calculation already. So we're going to start a new calculation, which is the 100 watts per square meter times the surface area, which is the 160 kilometers times the 40 kilometers. So I don't need the thickness, just the surface area on the top. And then both of them have to be converted to meters, so times 1,000, because this is an area here, 1,000 squared. Okay. Then the sun shines apparently for 12 hours. So the 100 is an average, just like it says, because the sun changes its angle throughout the day, so it's an average actually. So times 12 hours times 3,600 seconds in the hour. So every day it would absorb this much energy, 10 to the 16, 2.7 times 10 to the 16 joules. So I divide the amount of energy that it needs to melt the entire iceberg by the amount of energy that it receives every day. I can just put answer here, divide by answer, enter. So that's 17,720 days, which I then divide by 365 days in a year. Okay, 360.25 is what they said. There we go. And I come up with 48.5 years, just like the answer shows. And for some reason, again, they went through the kilocalories here. All right. I just made it quicker by just staying in joules. All right, the next problem is this one here. So, oh, okay, a little follow-up here. Number of years is amazing, but of course seawater is only melted. And then, yeah, again, I have this other iceberg here. And yes, it does take years to melt it. I don't know about 48 years, but it does take years. Let's see, rate of heat conduction of house walls, so that's the one I want to do. All right. Calculate the rate of heat conduction through house walls that are 13 centimeters thick and that have an average thermal conductivity twice that of glass wool. Okay. Assume there are no windows or doors. The surface area of the walls is 120 square meters, and the inside surface area is at 18 degrees Celsius, while their outside surface is at 5 degrees Celsius. So it's a, fall day in Alaska. How many, 1,000 watt room heaters would be needed to balance the heat transfer due to conduction? Then, of course, let's see, I'm going to actually trying to do it this way, so we can see it, the entire problem. So the way to do that then is to look up the specific heat capacity. Apparently for glass wool it's this much, 0.042 joules per second meters in Celsius degrees, multiply by 2 because it says doubles. Let's confirm that number, the 0.042 for glass wool. So I'm going to go over here, conduction, and it should be here. There should be a big table, there it is. And let's see where it says that. There it is. Yep, there's the 0.042 joules per seconds, meters, and Celsius degrees. All right, twice that much. Then the area is given here as 120, and then between the inside and the outside, it's 18 degrees minus 5 degrees, and then the thickness is 13 centimeters, which is 0.13 meters, and then the rest, of course, is just plugging in numbers. Let's see where I'm going to place this one here. Let's see, so 2 times 0.042 times the 120 times 18 minus 5 is 13, and then divided by 0.13 meters, which is 13 centimeters, and I come up with 1,008 watts, just like they have here, rounded, 1,010 watts. 1 kilowatt room heater is needed. Oh yeah, because it says 1 kilowatt room heater. How many of them? Just one. All right. All right, and the last problem for this section here. Let's see, it's this one here. Rate of heat conduction out of the human body. So calculate the rate of heat conduction of the human body, assuming that the core internal temperature is 37 degrees Celsius. The skin temperature is 34. The thickness of the tissues between them averages 1 centimeters, and the surface area of the human body is 1.4 square meters. So basically the same calculation. So here's the specific, here's the heat conductivity. So the 0.2 here, which is, tissue. I have to look up tissue in this one here. There we go. Fatty tissue without blood, 0.2. So that's where the 0.2 is coming from. And then the rest is given in the problem, 1.4 square meters. 37 minus 34 is 3, divided by 1 centimeter, of course, 0.01 meters. So that really is really similar calculation. I can go back to this one here, maybe. So it's a 2 right there. Oops, that's not true. Maybe I should have just typed the whole thing. 0.2 times 1.4 times 3 divided by 0.01. I guess I could have retyped the whole thing, but that's the same thing. There's the 84 watts. By the way, both of these problems here are Q per T, which means amount of heat per time, so which then gets us joules per second. So the power here that we have in watts is the amount of energy in joules that is being conducted per second. So heat per time, which here it's assumed that it's 1 second joules per second, which is the watt. All right. All right, so here are a couple of problems from chapter 15 on thermodynamics on engines, respectively refrigerators. So I'm going to start with this one here, heat engine on a gas-cooled nuclear reactor. Operates between hot and cold reservoirs of 700 degrees Celsius to 27 degrees Celsius. What is the maximum efficiency of a heat engine operating between these temperatures? And that would be then the ideal maximum efficiency is the Carnot efficiency. So I'm going to compute that. And I like to rewrite, actually I'm going to take this off here. I'm going to like to rewrite the efficiency as 1 minus the cold temperature divided by the hot temperature. You can see that here, hot temperature divided by hot temperature is 1 in the front, so 1 minus cold divided by hot. So 1 minus the cold temperature is 27 degrees Celsius. The hot temperature is 700 degrees Celsius, but as you know, for these absolute temperatures, we must use kelvins. It's not working in Celsius. So the 700 at 273, so 973, and the 27 at 273, you come up with a nice 300. That's possibly why they chose that. So there we go. 1 minus 300 divided by 973, which is 69.2%. And then they're saying here, compare that to the find the ratio of efficiency of a standard nuclear reactor. I guess a gas-cooled one is more efficient, 69%. So I'm going to go over here to this one here. So that's in that example, 15.4 in the openstax textbook. So here's a schematic of the nuclear reactor. Here's that equation that I prefer, 1 minus Tc over Th. They do it too. And here they come up with 47.6%. Notice that the temperature at which it operates 300 degrees Celsius or 573 kelvins is quite a bit lower than the one they gave us in the problem. Hence, the efficiency that we got is quite a bit larger. And then they go on explaining a little bit more here. All right, I'm going to give myself a break, and then I continue with the next one. All right, so this one here, an ideal refrigerator. Let's look at the original problem. Suppose you have an ideal refrigerator that cools an environment at negative 20 Celsius and has heat transfer to another environment at 50 degrees Celsius. What is the coefficient of performance? So this refrigerator, of course, is there in order to cool things, and the equation for cooling for the coefficient of performance is, for the ideal one, is right here. Divide the cold temperature by the difference between the high and the low temperature, so Tc divided by Th minus Tc. When we look at this one here, we can see that toward the end, Tc divided by Th minus Tc. So grabbing the calculator, I have 273 minus the 20, so 253 kelvins, of course from Celsius to kelvins, divide by parentheses. They didn't plug in the numbers here in parentheses, I do. So the high temperature is 273 plus 50, so 323, minus the cold temperature, or I computed that to 253 degrees. Somebody can say, well, that is 70. I don't even have to convert to kelvins. That's true because it's temperature difference, but I might as well do it anyway because these are all absolute temperatures and they ought to be in kelvins. Enter. There we go. There's the 3.61 for the coefficient of performance, which means this particular refrigerator, for every watt of power that you put in, electrical power that you put in, you are able to move, or for every 1 joule of electrical energy that you put in, you would be able to move 3.6 joules from inside the refrigerator to the outside, which then of course cools it because you move that much heat away. Notice that this is not a percentage. This is not 360%. It's not. What it means is that you, with a small amount of energy, you're able to move quite a bit more energy. It doesn't violate the conservation of energy. It's just the 3.6 joules already exist. You're just moving them somewhere else with less energy, with just 1 joule. So 3.6 is the answer. That's the coefficient of performance. It has no units because it's a ratio, actually. Their algebra here looks a little bit more complicated, and they're coming from this one here. Let's see, in the openstax textbook, there's that equation that they come from. They have they compare the coefficient of performance of a refrigerator to the coefficient of performance of a heat pump, and the two are related by subtracting 1. Basically, a refrigerator is a heat pump, an air conditioner is a heat pump, a freezer is a heat pump. It's just that they differ by that 1 here, and the reason is that in a refrigerator, you're taking heat out, you dump it somewhere else. For a heat pump, you're taking energy from somewhere else and dump it to where you want to heat it, and on top of it, you're also using the electrical energy, which then disperses as heat in order to heat your environment. And that's why the COP for the heat pump is 1 larger than the COP for a refrigerator. Notice when you move the 1 to the other side, it's a +1, and I think it's reflected here in this article right there. So the heating COP is 1 larger than the cooling one because of what I just tried to explain. All right, let's see what else they have here. And here they talk about heat pumps and refrigerators. Again, they're basically the same thing, moving heat from something that is already cold to something that is already warm. And of course, you use physics in order to do that. And let me see if there is actually, I think I have a schematic here. There we go. So that would be actually a schematic for a refrigerator. You use a coolant which absorbs heat from what is already cold and then dumps it as with the evaporation and the condenser, the evaporator and the condenser. It dumps it then into what is already warm, which would be the warm kitchen air, for example, for a refrigerator. All right, and I'm done for this unit.